power function is in the form y equals a times x raised to some power, where a and b are real numbers and b does not equal 0, because x raised to 0 power would automatically be 1, and if we just say y equals 10 feet, the wingspan of a prehistoric bony-toothed bird may exceed that of any other bird that ever existed. The animal weighed about 64 pounds and soared over the Chilean skies 5 to 10 million years ago. The wingspan of the bird can be estimated by this model. So L is the wingspan in feet, so how many feet long the wingspan is, equals 2.43 times W, the weight in pounds, raised to the 0.3326. We want to graph this function in the context of the application, so a window that fits and makes sense for the application. Use the function to compute the wingspan of a mute swan that weighs 45 pounds, and use the function to approximate the weight of an albatross whose wingspan is 10 feet 8 inches. So let's figure the context of this application. My W is my X, and the bird's going to need to weigh something, so between 0 and this was 64 pounds, so we maybe want to go to, let's say, 80 pounds. Okay, and the length, this is the Y. This big one was 17, so let's go between 0 and 20 feet, and that's the context we will use. So going to my calculator, we're using the function y equals 2.43 x raised to 0.3326. So that's the function I want to graph. My window, let's set from 0 to 80 for the pounds, and 0 to 20 for the wingspan. And look at our graph. All right. There's the graph we have. We have our graph over here, and we'll remember that we used from 0 to 80 for the weight, and from 0 to 20 for the wingspan. So now we have a graph of that function, the application. So compute the wingspan of the mute swan that weighs 45 pounds. So we're finding the length of the wingspan was 2.43 times 45 raised to 0.3326. And when I grab my calculator, I found out that it comes to 8.61915628. So let's round that to 8.62 feet for the wingspan of the mute fawn. Use the function to approximate the weight of the albatross whose wingspan is 10 feet 8 inches. Well, 10 feet 8 inches is 10 2/3 feet, or 32 thirds. So the wingspan is 32 thirds. It equals 2.43 times W to the 0.3326. So I'm going to divide by 2.4. So I'm going to take that 32 thirds. I'm going to divide that by 2.43. That equals W to the 0.3326. And what I'm going to do to find W is I'm going to take that 32 divided by 3 divided by 2.43, and I'm going to take the 0.3326 root of that. Now, as I go to my calculator, this is going to disappear, so it won't be when I come back to the page, but I'll show you how to use your calculator to find this. We want to take the 0.3326 root, and what I'm going to do is go to Math, and I'm going to come down to number 5. So I'm going to find this root, what I put in, find that fifth root. So I'm going to come down to number 5. So see, it's finding the root. Now, in there, I'm going to put parentheses. I took the 32 divided by 3, divided again by 2.43. Now close my parentheses and enter that. So it came out to 85.41156641 pounds. Okay. That is doing my calculation. And then we can also do it with a calculator. So I want you to go here. Let's go to our graph. And we want to find, I'm going to y equals the wingspan. I'm going to come down, and we want that wingspan to be 32 divided by 3. Enter that. And here's my graph, and you'll notice that comes and crosses, and it gets to the side. So let's 100. And now graph that. And you can see the line shows where it's crossed. So we're going to do second, the trace button, which is the calc. We want the intersection 5. There's where it is on the x curve, and x is 50. There it is, second curve, and x is 50. So I'm going to guess, say 65. Enter that. There it is, my 85.411566. So now we have two different ways that we can calculate that weight if we knew the wings. And that came out to 85.41 pounds. So that